Good morning, good afternoon, good evening, depending where you are in the world today. Welcome to today's webcast, which is the MicroGroove Advantage, Achieving High Energy Efficiency with Smaller Diameter Copper Tubes. This has been brought to you by the International Copper Association. Hi, my name's Nigel Cotton. I am the OEM team leader for the International Copper Association, and I'm your moderator for today. Before we begin today's presentation, I would just like to make a few announcements. This webcast is designed to be interactive, which means that you can participate in the questions and answer session by asking questions at any time during the presentation. Just type your question into the Q&A widget to the right side of the slide area window, and then click the submit button to make your question. You may adjust the area of any widget, such as the slide area, by clicking on the lower right-hand corner of that widget window and dragging the mouse. The slides will automatically advance throughout the event. If you're experiencing any problems with this program, please refresh your browser or close your window and relaunch the presentation. You can also visit our webcast help guide by clicking on the question mark button on the docking bar at the bottom of the console window. Okay, so now we're going to move on to the presentation, the MicroGroove Advantage, Achieving Higher Energy Efficiency with Smaller Diameter Copper Tubes. And discussing today's topic is John Hipchen. John Hipchen has over 14 years of experience with heat exchanger technologies, including the marketing of copper alloys as well as manufacturing technologies for brazing and soldering. Previously, he managed the development of new markets for specialized equipment systems. John graduated from the Loyola University in Chicago and spent his early career working as a chemist. Okay, without any further ado, I would like to give the floor to John Hipchen.
All right, thank you, Nigel. And on behalf of the International Copper Association and all its affiliates and copper centers around the world, I'd like to welcome everyone to this webinar. As representatives of the copper industry, our goal today is to make you aware of emerging trends, to help you understand what is driving these changes, and to explain the technology behind them. We also want to show you energy-efficient options that will help meet the demands being placed on our industry. This webinar will take us through the basic technology behind heat transfer and explain the benefits of smaller diameter copper tubes in refrigeration and air conditioning coils. There will be another webinar next week that presents different information, focusing more on system-wide designs, case studies, and energy efficiency issues. Our member companies who produce copper tubes can provide even more information about specific tube products and supply solutions. And toward the end of this presentation, we will post the microgroove.net website where you can find detailed technical information as well as information about suppliers and upcoming webinars. The type of coils we're going to talk about today are round copper tube flat fin coils, and they are used in a number of applications that cover residential, commercial, and industrial settings. These coils can be condensers, they can be evaporators, water heating coils, and a number of other heat exchanger uses. Round tube flat fin coils have been around for over 100 years, and there are good reasons why they are still in use today. But as we're going to see, they are being successfully modified to fit modern demands. Many of us are already familiar with the increasing requirements for energy efficiency and the push to use refrigerants that are less damaging to our atmosphere. In an effort to lower costs, many design engineers are also under demands for smaller, more compact systems that save on materials and refrigerants. So over the next 60 minutes, we're going to discuss these demands for efficiency and cost savings. And we are going to look at how smaller diameter MicroGroove copper tubing can help meet these demands with a minimal investment or change to our well-established manufacturing practices. This photo is taken right out of a current catalog of heat exchangers, and it's a good example of the changes we are going to discuss today. The new design in this picture shows smaller diameter tubes that not only provide 35% more passes, which will result in considerably more heat transfer, but you'll notice that the tubes are arranged in a staggered pattern, which will again improve the efficiency of this coil. And this is a good representation of the trend that we want to discuss in more detail. Specifically, we're going to show how reducing the diameter of copper tubes can improve heat transfer, resulting in more energy efficient, smaller, and lighter coils, bringing about all of these benefits to the manufacturers and distributors of air conditioning and refrigeration systems. Keep in mind that each of these benefits is not only associated with meeting energy and refrigerant regulations, but each benefit also means cost reductions or cost efficiencies that help all of us in this increasingly competitive market. As I mentioned, the standard round tube plate fin coil has been in use for over 100 years. In the 1980s, tubes with internal grooves and enhancements were developed, and because these internal modifications were found to have such a big impact on efficiency, they quickly became common in the market. The name MicroGroove today refers to these internal enhancements. But MicroGroove is a newer name, and it also means smaller diameter tubes. Over the past 10 years, we have seen a trend toward internally enhanced, smaller diameter tubes, and on this timeline we noted that coils with MicroGroove tubes have been in commercial use since about 2005. And we know that all of these OEM manufacturers are currently producing systems with small diameter MicroGroove tubes. There are a number of factors behind the move towards small diameter tubes, and they range from government mandates on energy efficiency, such as increased SEER ratings, to the phasing out of R22 refrigerant and higher pressures that are associated with replacements for R22. R22 replacements include 410A, which is currently being used in residential air conditioning systems. The coefficient of performance, or the COP, is another rating that design engineers are paying more attention to, and the drive to increase COPs is yet another factor behind trends towards smaller diameter tubes. About 20 years ago, government regulations became a larger factor in the design of air conditioning and refrigeration equipment when the Montreal Protocol took effect, and that happened in January of 1989. Since then, that's undergone 7 revisions. The Montreal Protocol mandated a phase-out plan for CFCs, which are chlorofluorocarbon refrigerants, and they mandated that phase-out by 1995. So this covered refrigerants like R12 that are no longer used. HCFC refrigerants, which are hydrochlorofluorocarbons, were allowed as transitional replacements until HFC refrigerants are fully implemented. And HFC stands for hydrofluorocarbon, and this family of refrigerants does not have chlorine, and chlorine is the problem element which has been linked to the depletion of our ozone layer. R22 was a transitional HCFC refrigerant, and today we see this being replaced by HFCs like 134A, 404A, and 410A. It is typical for HFC refrigerants to operate at a higher pressure than CFC or HCFC refrigerants. In R744, that's the name for CO2 as a refrigerant, and systems that use CO2 have even higher operating pressures. In Europe, a directive that is often referred to as the F-gas regulations banned the use of 134A in new automotive platforms, and that was scheduled to start this year in 2011. The Coil protocol was adopted in December of 1997, and that went into effect in 2005. And the Coil protocol adds to the phase-out of CFC covered by the Montreal Protocol, and it focuses on greenhouse gases and HFCs. To quickly summarize this slide, government mandates that are related to energy efficiency and refrigerant use have pushed air conditioning and refrigeration manufacturers toward new coil designs that have to be more efficient, and they have to handle higher pressures. Before we get into the technology of refrigeration and air conditioning coils and the technical reasons behind the trend to smaller diameter tubes, we want to emphasize just how complicated this subject is. We have refrigerant that's moving through coils, and as it does, the refrigerant changes phase from vapor to liquid, or vice versa. In the process, we have heat being transferred from the refrigerant through the tubes to the fins and ultimately into the air. And finally, we have the air that's moving across the fins and the heat that's being dissipated into that air. In all of these segments, we have dynamic processes occurring. So the math behind the design of a coil can be quite lengthy and complicated. So for the purposes of this discussion, we're going to concentrate on technical concepts, and we'll use images to make our points. We plan to avoid any heavy math today, but we could go into that level of detail in a separate meeting where we would have sufficient time to do so. So let's review the path that heat takes and the mechanisms involved as it moves from the refrigerant inside of a tube, through the tube wall, into the fins, and finally into the air. This slide illustrates heat flow in a similar manner as electricity, with areas of resistance. So if we start on the right, inside the tube, refrigerant carries heat and moves that heat into the tube wall. Conduction transfers that heat through the tube wall, where it either continues to move into the fins, or the heat can be transferred into the air, moving across the tubes by convection. The heat that has been transferred into the fins is eventually transferred into the air by convection. So we see areas where both convection and conduction are the mechanisms at work transferring heat. Now let's take a close look at exactly what happens to the refrigerant flowing through the tubes, because that's where all of the heat transfer begins. Whenever fluid moves through a tube, the fluid that's closest to the tube wall behaves differently than the fluid in the center of the tube. The fluid that's next to the tube wall sets up a boundary layer where heat transfer becomes more difficult. And this applies to the hydraulic motion of fluid as well as the way heat moves from the center of the tube to the tube wall. So heat transfer engineers refer to both hydraulic and thermal boundary layers. To simplify, the fluid closest to the tube tends to move slower than the fluid in the center. And even in turbulent flow, a laminar sublayer forms, and heat moves slower through these boundary layers than it does in the fast-moving fluid toward the center of the tube. Boundary layers act as an insulator, and they interfere with the heat transfer that we want. The internal enhancements in MicroGroove tubes, in other words, the grooves and the proprietary patterns that tube manufacturers put on the inside tube wall, they reduce this boundary layer and they increase heat transfer through the tube wall. Here we can see the boundary layer in a smooth tube develop, and it does not dissipate or go away. But in a tube with MicroGroove enhancements, you can see that the boundary layer begins to develop, but it breaks down as it moves over the grooves. The exact configuration of internal grooves and patterns is based on a long history of technical development and design, and it's backed up by both experimental and field performance data. And the data clearly shows significant advantages to MicroGroove tubes. The additional mixing of the refrigerant that occurs inside the tube because of these grooves increases the amount of refrigerant that comes in contact with the tube wall. The positive effect on heat transfer from these internal enhancements has been known for a long time, and it's been applied commercially for over 20 years. And when combined with small diameter tubes, we have even more advantages that we want to look closer at. But before we do, let's look for just a minute at how air flows through a round tube coil. Air must flow around the tubes as it passes through a coil, and as it does, the airstream is broken up and heat is transferred into the air. The number of tubes and the location of the tubes, as you can imagine, will have an impact on the air pressure that is lost going through the coil. Air forms the same type of boundary layers as refrigerant does, and in many respects, it can be dealt with the same as any fluid. Just as we saw with microgrooves inside of the tubes, outside, the tubes break up any boundary layers that the air tends to form as it flows through the coil. The more tubes we use, the more we break up the boundary layer on the air side, and more heat transfer will result. But in many cases, more tubes means a higher airside pressure drop. So there's a balance at some point where a coil uses an optimal amount of air to achieve the heat transfer that the system requires. Remember also that heat is being dissipated by the fins, and the fins have slots or louvers, again, to break up boundary layers and improve heat transfer. Now let's discuss the geometry related to a reduction of tube diameter. And while we do, keep in mind the fluid dynamics that we just looked at and the advantages of microgrooves. When we compare tubes of different diameters, the first thing we might notice is that it will take several smaller diameter tubes to equal the surface area of a larger diameter tube. And at first glance, we might think this is a disadvantage, but we actually have some important benefits here. A big one being an increase in the surface area to volume ratio, and that equates to more heat transfer. And with this increase in heat transfer, we don't need to match the volume or surface area of the larger tube to get the same amount of cooling. Another benefit that we haven't mentioned yet is that in a smaller diameter tube, we can hold the same pressure as a larger diameter tube, but we can do it with thinner walls. So when we reduce tube diameters, we can actually reduce the weight of the materials being used, and that in turn reduces costs. And as we continue to reduce tube diameters, we continue to gain surface area in relation to the amount of refrigerant that we have in the tube. And we can continue to reduce tube wall thicknesses while still meeting the same pressure criteria as the larger tubes. Or, if you look at it from another angle, we can handle higher pressures in a smaller diameter tube with the same tube wall thickness. The bottom line is that we can do a whole lot more with considerably less material. To demonstrate this a bit further, we're looking at a plot of surface area over volume. As we go from 9.5 millimeter diameter all the way down to a 3 millimeter diameter tube, you can see that the amount of surface area that is available in the same volume increases dramatically. And that is why the heat transfer coefficient is so much higher in smaller diameter tubes. It's because there is more surface area available to transfer that heat. So now we want to start talking about what happens to the entire coil when we substitute smaller diameter tubes. For the person that's designing coils, there are a number of factors that can be considered. And all of these factors will have an impact on things that people who buy these coils are interested in, such as how big they are, how much energy they use, and how much they cost. So there are options when it comes to designing coils, and we want to look closer at some of these options to see exactly what the effects are on performance. So let's adjust these parameters. First, the total length of the tubes. Secondly, the amount of surface area. And third, the volume of refrigerant. And the effects we are interested in when these parameters change are, number one, the overall performance of the coil as measured by the amount of heat that can be transferred. Number two, the weight of the coil, because that correlates directly with material cost. And number three, the heat transfer coefficient or coefficients, if we remember the thermal resistances in the earlier slide. For this discussion, we will reduce the diameter of the tubes. And without getting into a lot of numbers, let's take a look at a chart that shows the effect of changes to these parameters. This chart shows different scenarios. And in each case, we're reducing the diameter of the tubes. And in each scenario, you can see that one of the parameters is held constant. Let's look first at what happens when we hold the total length of tubes constant, but we reduce the tube diameter. What we're talking about here is not the length of each individual tube, but if we add up the lengths of all the tubes, we get a total tube length, and that is what we're referring to. If we match the total tube length, we see a decrease in surface area, a decrease in volume and weight. The heat transfer coefficient increases, but the drop in surface area is such that the system cannot match the original performance, so that performance drops. And this would amount to considerable cost savings due to the low refrigerant charge and the reduced materials, but depending on the application, that drop in performance would probably not be acceptable. So in the second column, the performance is held constant, but in order to achieve that, the total tube length was increased. We have considerably less surface area than the original coil, and also much less volume, less weight, and a higher heat transfer coefficient. So in this scenario, shows a coil that matches the performance of the original, but it's smaller, it's lighter, and it has a lower refrigerant charge. And very important to a lot of people, it'll have a much lower cost. In the third column, the surface area is held constant, and that means the total length of the tubes will increase. And if we use the same tube wall thickness as we did in this chart, it works out that the weight is about the same. But I want to point out that when we match the surface area with smaller diameter tubes that have typical reduced wall thicknesses found in suppliers' product catalogs, we actually see a reduction in weight. The volume will decrease and the heat transfer coefficient increases, again due to the tube efficiency. So in this scenario, performance increases considerably, and costs are reduced because there's less refrigerant. In the last column, the volume is held constant, and that means the total length of the tubes is increased much more than the other scenarios. The surface area increases, and so does the weight and heat transfer coefficient. However, in this scenario, the performance goes up dramatically. Although a cost increase would be expected in this scenario because these coils will use more materials, that cost is buying a big increase in performance. So now that we've looked at some theory behind the benefits of microgrooves and small diameter tubes, let's remember again the factors that are driving our market right now. As design engineers grapple with these changes, they realize there are benefits of smaller diameter microgroove tubes that have not yet been fully exploited, and these benefits could solve a lot of the problems they were dealing with. Specifically, the increase in surface area to volume ratio from microgroove tubes had a big impact on the heat transfer coefficient. Plus, smaller diameter tubes could stand higher pressures with thinner tube walls. And this gives the people that design coils some options. First of all, coils can be designed to take up the same amount of room but have considerably higher performance and handle higher pressures. And this is important if pressures produced by the compressor have gone up to meet new SEER ratings. Or another option is to design coils that take up less room and still have higher performance than coils with larger diameter conventional tubes. Coils can be designed with smaller diameter microgrooves to match the performance of an existing coil, but take up much less space, and due to thinner tube walls, material costs and refrigerant charge would be lower. Or coils can be designed with a lower airside pressure drop. All of these options are valuable, and depending on the goals of the project, and all options have the potential to reduce costs. There are yet more options available, but this gives you an idea of the design flexibility that results from microgroove tubes. Now let's talk about manufacturing coils with smaller diameter microgroove tubes. Shown as simply as we can, a typical coil is made of tubes and a series of flat plates. The tubes are inserted through the plate fins, and fin spacing is maintained by the size of the collar that's formed around the holes for the tubes. Fins can be stacked prior to the placement of the tubes, and the collars around the tube holes will hold the fins at equal spacing. The tubes are then expanded in diameter, and this binds them to the fins mechanically. This expansion of the tubes produces a contact between the tube and the fin, which is critical to the transfer of heat. In this photo, you can also see the louvers in the fins. And remembering our discussion on boundary layers, these louvers increase heat transfer by breaking up the air and eliminating the formation of boundary layers. You'll also notice that the tube ends are flared for U-bend fittings. U-shaped fittings are brazed onto the tube ends, and this determines the exact circuit that the refrigerant will travel through the coil. The brazing material is often supplied as a solid ring that slips onto the joint during assembly, and that ensures that a consistent amount of material is used in each joint. This is a well-established process, it's very reproducible, and it's very robust. This method of manufacturing coils continues to set the industry standard for corrosion resistance and reliable service life. Since this process remains largely unchanged for small diameter microgroove tubes, engineers and technicians throughout the industry are familiar with the practices and also the costs associated with it. So now let's take a look at actual situations where small diameter microgroove tubes were used and the resulting data that was generated. In China, a small diameter copper tube research consortium was formed, and their results have served as a foundation for the development of residential air conditioning products that are more economical and use less material than traditional technology with conventional tubes. Wenson Zheng, Frank Gao, and Kerry Song, all from the International Copper Association's Shanghai office, co-authored 4 research papers on small diameter copper tubes, and they did that in cooperation with 2 Chinese universities. They collaborated with the School of Energy and Power Engineering at Xi'an Jiaotong University on heat exchanger design projects. And they collaborated with the Institute of Refrigeration and Cryogenics at Shanghai Jiaotong University on the condensation of refrigerant oil mixtures in small diameter tubes. In addition to research papers and projects at universities, air conditioning and refrigeration OEMs recently published 3 papers on small diameter copper tubes. Researchers from Chigo Air Conditioning reported on the performance of small diameter copper tubes in an evaporator for residential air conditioners. Researchers from Medea Refrigeration Appliances reported on small diameter intergrooved copper tubes in a split air conditioning system. And researchers from Luva in Italy presented geometry for the next generation of condensers with an ultra-low refrigerant charge. All of this information can be found at our MicroGroove.net website. Now let's take a closer look at exactly what they found and why small diameter copper tubes provide so many advantages over conventional technology. The next few slides use data from the research consortium, and this data shows the effects of small diameter tubes in real numbers. We mentioned that the heat transfer coefficient in the tube increases as the tube diameter decreases. In this experiment, the heat transfer coefficient is measured for 5 millimeter and for 4 millimeter microgroove tubes. The heat transfer coefficient is reported in watts per square meter Kelvin and is plotted against mass flux reported as kilograms per square meter second. You can see the higher heat transfer coefficient for the 4 millimeter tube tracking about 15 to 20% above the 5 millimeter tube. The effect of the grooves and internal tube enhancements on heat transfer coefficients can be seen here, measured in 5 millimeter tubes at 3 different mass flux rates. Remember that the grooves break down the insulating boundary layer that we talked about and mix refrigerant as it moves through the tube. The effect on the heat transfer coefficient when compared to a smooth internal tube surface is rather significant, as seen in this data. It's interesting here that as the mass flux increases, there's a positive effect on the smooth tube regarding the heat transfer coefficient, but there's a much more significant effect on the microgroove tube. One thing that we must be aware of is that it takes more pressure to move fluid through small diameter tubes than it does through larger tubes. If the hydraulic pressure is measured before and after fluid moves through a tube, a pressure loss or a pressure drop is measured. and this pressure loss is plotted here, measured in a core with 7mm tubes and one with 5mm tubes. At 3 different flow rates, a slightly higher pressure loss can be seen in the smaller diameter tube. Pressure losses can be easily reduced with an increased number of branches. In fact, if the number of branches is increased, the tube length per branch can be decreased, and that provides extra options to the heat transfer engineer. Comparisons are often made between round copper tubes and aluminum microchannel tubes. Be careful that the copper tubes in the comparison you're looking at are microgroove. As you've already seen, just comparing copper tubes with smooth internal surfaces to enhanced internal surfaces shows big effects. Comparing conventional, larger diameter, smooth copper tubes to aluminum microchannel tubes will also show favorable results for microchannel. However, when the comparison is made to smaller diameter copper microgroove tubes, the copper tube is not only competitive, but it's often superior. Comparison studies often cite a high airside pressure drop as a disadvantage for copper tubes. However, we must remember that both the tube geometry and the fin design are responsible for the airside pressure drop. With copper tubes, there are a number of options, such as the number of tubes, how the tubes are arranged or the tube geometry, and lastly, all the parameters that go into the fins, such as the fin pitch, louvers, louver angles, etc. Microchannel tubes allow only one path for air, and therefore the only parameters that are left to deal with airflow are the airflow and the airside pressure drop are those that are related to fin design. On the refrigerant side, remember that the circuitry of copper microgroove tubes can be modified to adjust refrigerant pressure drops. A big advantage for microgroove tubes is the lower refrigerant charge. Aluminum microchannel tubes are all joined at a manifold that can take a considerable amount of refrigerant to fill. So let's take a look at a report by an Italian company named Luva that was presented last year at a workshop on refrigerant charge reduction, and that was at a conference in Stockholm, Sweden. In an effort to optimize an existing condenser with conventional 9.52mm tubes, or 3/8" tubes, this Italian company designed new coils, keeping the performance the same, all around 20 kilowatts, and that's highlighted in the chart. As I mentioned, their existing coil had 9.52mm tubes, and in the trial designs, they used aluminum multi-channel tubes and 5mm microgroove tubes. In this row, you can see that they were able to reduce the refrigerant charge in the aluminum tube design to about 51% of the refrigerant used in the existing design. But the 5mm copper tube design only used about 44% of the refrigerant compared to the original design. So that further reduced the refrigerant charge another 16 or 17%. If we look at the size of the header required in the aluminum design, we can see a diameter of 38 millimeters. And the company reported that as the minimum diameter that they could use to ensure proper tube-to-header joints and refrigerant flow. So this is a good example of the advantages that copper microgroove tubes offer over conventional designs. Engineers have continued to work with microgroove tubes, and today they are seeing additional options that have not been tested yet, but have the potential to change air conditioning and refrigeration coils even further. So in conclusion, I'd like to review these basic benefits related to small diameter copper microgroove tubes. Small diameter microgroove tubes allow for energy efficient designs. They allow manufacturers to use less material and less refrigerant, and these are proven, durable products with a history of success behind them. Small diameter microgroove tubes allow engineers the flexibility to design for a wide variety of operating conditions. And this is a manufacturing process that's proven, it's economical, and it's robust, and is familiar to the entire industry. And finally, this process is supported by a supply chain that's very well established with manufacturing and distribution centers worldwide. For more information, as I mentioned earlier, you can visit our website at microgroove.net. And that concludes the formal part of the presentation. I'd like to thank everyone for their attention. And now you can submit questions. And at this point, I'm going to turn it back over to Nigel Cotton, our moderator.
Okay, thank you, John. Now's the time for the question and answer part of the webcast. So a reminder to you out there is the way to participate in the Q&A is to type your question into the Q&A widget to the right side of the slide area window, and then simply click the submit button. We do have some questions in. We have, to you, John, is this technology applicable for 3/8 inch tube only?
No, the technology that, 3/8 inch or 9.52 millimeter tubes are very common especially in North America, and it's applicable to any tube diameter, but it's been applied mostly to the conventional 3/8 inch tube. But most of the work has been done down to 5, and as you saw, 4, even 3 millimeter tubes. But typically, so far, what we've seen in the industry is it's being applied mostly to the 3/8 or 9.52 millimeter tubes.
Is the microgroove the same as the inner groove design? I'm not quite sure what that really means, but is there a difference between microgroove and other groovings?
MicroGroove is a general name that's given to smaller diameter copper tubes with internal enhancement. So it's fairly synonymous. MicroGroove and inner groove just refer to the fact that the tube has internal enhancements.
Okay, thank you. What is the recommendation for tube thickness for R410A condenser coil?
Well, the best place to get that answer would be from the tube supplier, but typically I think we see tube thicknesses around a little more than maybe 0.2 millimeters in a 5 millimeter tube, and that's down considerably from the 0.28 that you might see in a 9.52 millimeter tube.
Okay. There's still an opportunity to write your questions into the Q&A box. So if you have a question in mind, please feel free to do that. Obviously, we've got the website for further reference, and we would be happy to take contact through the website if you wanted to speak to an expert. The next question on the list is, who supplies small diameter microgroove tubes, and where can I buy them?
Well, small diameter tubes are currently in production, and they're being shipped to a number of major manufacturers worldwide. All the tube manufacturers in North America and the EU have the capability, and they also have the desire to provide small diameter tube when their customers require it. So I would advise consulting your current supply base for specific information that would be related to the availability and also pricing.
Okay. And if we go to the website, there's an opportunity to see a supplier directory there. Okay, I have another question in. Does refrigerant type alter the MicroGroove design, or are they standard for all types?
Again, that would best be answered by the tube supplier, but it's going to depend on the pressure that the refrigerant requires, the operation pressure, and that will in turn dictate how much tube thickness is going to be required at a particular diameter.
I think we're at the point of just one or two more questions. So if you have a question in mind, please submit it in the next minute or two. I think going through here, is it possible to use MicroGroove in large commercial units, taking into account the problem of pressure drops? Large commercial referring to chillers, external units.
Sure. It is possible to use smaller diameter MicroGroove tubes in larger commercial units. And it's going to depend, as I mentioned, you can add paths. There are a number of things that the designer or the heat exchanger can do to handle the pressure drops. And you could contact the International Copper Association separately from this, and we could help direct you to people that would help you with your specific project.
Okay, I think I've got a follow-up question. Is it suitable for larger tonnage capacity units? This came from Zemil Air Conditioning.
Yes, it would also be suitable for larger tonnage air conditioning units, and the same factors that I just mentioned would apply to that as well.
Okay. Which is the maximum operating pressure?
I don't know that that's really been established yet. There seems to be a tube for every pressure that we've encountered so far. So at the moment, I don't know that there's a maximum. And again, if you've got a specific project in mind, I would encourage you to direct that either to the tube supplier themselves or to us, and we can help you get in contact with people that'll match up the correct tube and tube diameter for that pressure and application.
I've got a question because, and I think the author was a bit unsure whether it had been covered in the slides, but he was saying, has this been used with CO2 systems?
Yes, I believe it has, and it's certainly capable of that. The smaller diameter tubes can handle higher pressures with thinner walls than larger diameter tubes. So it's actually a very good candidate for CO2 systems because of their higher pressures. It would handle those pressures with less material.
Okay, there's a further question here. What about the oil? What is the effect of the grooves? The
oil does have an effect on heat transfer, and there's actually a paper on our MicroGroove.net website that addresses that. But it does decrease the heat transfer, and that has more to do, I think, with the oil being in the refrigerant than it does with anything specific with the grooves.
Okay. I've got one question here. Is it possible to have the presentation slides afterwards? Yeah, at the end of the presentation, I will mention how you can get the presentations, and if you have a problem, you can always drop an email to the website, and we'll happily sort that out with you. I've got a question here. Can MicroGroove tube compete on a cost level with MPE aluminium tube?
So far, we believe it can, yes.
Yeah, I think it's for those guys that know the true costs to go away, work them out, recognize that there's other benefits from knowing about copper, having experience with copper, and not having to change the factory footprint too much. But certainly, we wouldn't be in the game if we didn't think we had a good chance. So
absolutely,
we welcome any opportunity to put that one to test. Okay, we're getting, I think, quite close to the end of our time, and also to I've just got another question in here, but one question stands back: is the fin geometry, space, etc., a factor in influencing the heat transfer?
Without a doubt, fin. All the factors that go into a fin, the spacing, the louvers, the angles of the louvers, those all influence the heat transfer capacity of the coil. So that works in conjunction with the tube diameters, and the spacing of the tubes.
Okay. All right. I think I've pretty much covered them all now. We had one on supply earlier, I believe. What kind of manufacturing changes, if any, might be required for smaller diameter tubes?
Well, the manufacturing process for small diameter copper tubes is the exact same process that's been used in our industry for a long time, and it's been used successfully. So it's a process that just about everyone is familiar with. And companies planning to switch to smaller diameter copper tubes, they'll be able to use all their existing production equipment with very minor modifications to the tube expansion equipment. And they'll still be able to supply the market with the same durable copper tube products that they always did, but they'll use less material, and they'll be more efficient because of the smaller diameter copper tubes.
Okay. I've got a quick one here. How can we manage the extra pressure drop from small tubes?
Well, the higher pressure drop is easily managed with adding either more paths, and that's probably the primary way to handle that. The addition of more paths usually takes care of the pressure drop. You might have to increase the number of tubes as well.
Okay. I mean, getting a couple of specific questions here that I think probably need an expert advice. How should we approach, or how should one of the attendees approach getting further information, do you think?
Probably the best way to start would be to drop an email at the MicroGroove.net website, and as you mentioned earlier, Nigel, we would respond to that as quickly as we could.
Okay. I think we've got a series of questions now in front of us. Some of these are repeats of previous ones, but where if you've left your details and a question, we will certainly try to get back to you after the event and satisfy your answers. And that would also lead to the fact that next week we also have on the 22nd a further webinar, which has some more details and some more information. Is a further update of the information you got here today. Okay, I think I've probably got a minute left, and I'll have a quick look through here for additional questions. So yeah, they've pretty much been covered before. We had the question on what was the tube thickness, I believe.
Yes.
Yeah. Okay. And all right. So I think if there's any pressing questions that you don't feel have been answered, please go to the Q&A section now, put them into the list. And although we won't be able to answer them now because I think the session is drawing to a close, we will be happy to follow up with those later. So it's for me to now say thank you to John particularly, but thank you to everybody that's attended this seminar on MicroGroove Advantage, achieving the higher energy efficiency with smaller diameter tubes. Within 48 hours, this presentation will be available on demand. You will be able to receive an email once it is available. On behalf of all of us here, including John, I would like to thank you for attending. I'm Nigel Cotton, and I'd like to thank you for your time and wish you a very pleasant day. Thank you.